Hello everyone. Today I'm going to be doing a presentation on the effects of topography and hydrology on soils that are in the same geographical area. So let's move on to our first slide, see what our study area is. Here, as shown on the Google Earth image profile created from it, is our study area. The area is located in the town of Rodeo, California, and an area that is assumed to be undeveloped by the Parker Avenue and Highway Interstate 80. And what we have here is a creek, medium-sized creek that never runs dry, that flows through the town of Rodeo. And it flows in this V-shaped depression, V-shaped channel to the left and to either side of the channel. Once that, as we can see on a cross section, we have this flat area that is presumed to be a floodplain of a river, where deposits would eventually accumulate from the creek overflowing occasionally, and by the erosion of the hills that are on either side beyond this flat area. Unfortunately, most of the town of Rodeo is built up in this area, and this is the one little section where within 100-200 meters of either side we can take samples of soil that are geographically in a same location. There shouldn't be a difference in parent material. Most of it is a sandstone, although there's some pinole tuffs. In the area, there are a couple of outcrops that one of them is on a hill by the site 4, and one of them by the site 2 under the tree. There's a rock outcrop, and both of them are sandstone. So we presume that parent material for the area is similar or the same. So the only factors that would differentiate between each site is the topography and hydrology. Topography related to erosion with material moving downhill, and hydrology is how the creek moves the sediment and deposits it or washes it away. So that we have our sites marked as site 1, that is taken by the edge of a creek. Site 2 is taken on a slope of the river channel, just a couple meters away. Site 1. Site 3 is taken on this floodplain area. I would call it a floodplain area. And site 4 is taken across Parker Avenue, where the hill begins to slope up. Now let's move on to the next slide so we can analyze each site and see what we find. But before we go on, these are our procedures that were used. We used a soil auger to take one core up to 1 meter deep at each site. Then the horizons were identified, and where the quantity of soil permitted, we ran the test using hydrometers. We had to have a 50 grams of dry soil that was then screened, crushed and screened to remove anything that's larger than 2 millimeters, as it is not a constituent of soil. Then it was mixed with a solution of deionized water and 5 milliliters of Calgon solution. make sure that the clay particles do not stick and act like larger particles. So that was done, and samples were placed in this large graduating cylinders, overturned a couple of times to stir up the sediment. Temperature was taken, and hydrometers were placed to see the change in density. And as at the beginning of all the sediments were suspended in the water, we had reading. The sand, of course, being the largest particles, would drop down within the first 40 seconds, and as it settles to the bottom, the density of water changes, and hydrometers begins to sink further deep into the mixture. Then the next reading was taken after 2 hours, since we assume that within 2 hours, by the size, the silt particles would settle, and the only thing that would be left suspended in the water is clay. And by using these readings and against a reading of a hydrometer in a clear deionized water, we can then calculate the percentage of silt, clay, and sand, and this where we did not have enough soil to do it for every location and every horizon, but the most important ones, we had a lot of clay. We wanted to distinguish. We did. This was at site 1, at site 2, and the A horizon of a site 3. But we'll see more details on the further slides. So let's move on. This is site 1. Site 1, as you can see, it is a steeply banked river channel, and there's my daughter. She's hammering a soil probe right by the water's edge. We went down all the way to 1 meter, and based on what the water level in the creek was, about 1 meter of it, I'm sorry, about 50 centimeters of the soil taken would be above the current water level, and the further 50 centimeters would be below the water level. We can see 2 very distinct horizons, although by the color they are very similar. The A horizon had a very strong granular structure and easily compressed, as you can see, even though that measuring tapes shows the area that's sort of been compressed. As we were driving the soil auger, it was so loose that it compressed that part of the soil. However, we see that about 67 centimeters deep, the granular structure of soil changes, and you can also see very perceptible change of grayish and brownish soil, which is assumed to be some evidence of modeling. That was actually a surprise to me, because since this creek never runs dry and we are right by the water's edge, I thought that we might find some clay condition of iron that is gray in color, since it's always wet. The surprise, however, that we did not find it. So that was a surprise in this location. And since we have an A and B horizon, we took the texture analysis for each of the samples, and we analyzed them. We will see it on the next slide. Okay, so here is for the site 1 texture analysis. On the right, first of all, just to visualize, is not as accurate as the method hydrometer. We took soil, we crushed it, we mixed it very well, shook it in a test tube, and allowed it to settle for 3 days, and we can see that there's quite a large amount of sand. This is the A horizon, and then see it turns to smaller particles and silt, and then there's some clay. However, the texture analysis using the hydrometer showed us that the A horizon has a 26% clay content, 38% silt, and 36% sand. And the analysis using the same method of a B horizon gave us 22.4% clay, 32.8% silt, and 44.8% sand. So as we go deeper, we'll expect to find more clay. However, it was getting sandier. Maybe we're getting close to the bedrock, to the crushed parent material, perhaps. But this was the results that gave us. That was a bit unexpected for this particular site. So let's move on to the site number 2. Site number 2, as you can see, we went up the slope of the river channel. It's about 2 to 2.5 meters above the watermark, and maybe 4 meters away from the first core. There, we had a drastically different soil, although it's very, very close. And it was significantly darker, significantly harder. Again, perhaps there were more horizons, but the one that I was able to identify was the A and B horizon. The A horizon ran from surface to 54 centimeters, and the B horizon ran deeper than that. The way I could identify it is all of them was dark and silty and also clay rich. But the A horizon had some gravel. That, however, I would not attribute to natural process. Perhaps to the left of the image where you see the auger sticking out of the ground, there are some their fence in their backyard. So perhaps while moving the soil, that's where the gravel ended up. Maybe. However, the deeper horizon in B is definitely natural and very dark, very hard, and very sticky when wet. It was very difficult to drive the soil probe to its full depth and then extracting it. That is assumed that as the river would, during heavy rains and high tides, would rise, the level of the water would rise up, even though it wouldn't overflow its river channel, but it would be high enough to deposit silt on its on the banks of this river channel, and that is what I interpret this dark layer to be. Let's see what analysis of this layers gave us. So the texture analysis of the A horizon that I assume was somewhat affected by the human activity had 31% clay, 33% silt, and 35% sand. So pretty much equally distributed almost of sand, silt, clay, silt, and sand. The B horizon, however, we can clearly see that we have more clay, and although in percent it's not a huge difference, it was perhaps different type of clay. Maybe we have more of a 2-to-1 clay, that make it very sticky. The mixing and then letting the sample settle, as we see on the right, that was an A horizon, does not show that much sand. It appears to be less sand. So it's just visualization. We should trust more in a more precise method using hydrometer that give us results that we have. So this was to be expected. I did not expect to find a clay condition. I expect to find quite a lot of silt and clay, and that's what we did find in this location. So let's move on to the site number 3. That is site number 3. See in the background on the picture, that's a Highway 80, and to the right, crossing it is Parker Avenue, and there's my daughter holding the soil probe where we're about to take the core sample. When we took the core sample, again, this was distinct. We identified 4 horizons. We identified a horizon that was quite extensive. It ran from 0 to about 65 centimeters. It was granulated, and as you can see, also compressed quite a bit as we were driving the soil probe. Then we had 3 relatively distinct B horizons. One ran from 66 to 78, from 79 to 92, and 93 plus centimeters. In particular, what is notable was the third B horizon, that is at the very right end of a soil probe. You can see it is getting very sandy, so it was very distinct. But it also shows that in this there are these distinct layers. I could not determine whether this distinct layer were the result of a human activity, perhaps grading of the area, but these are the results. We just presume that this is undeveloped because knowing the history of the area, there had not been any structures built here. However, it was occasionally used as a lot for construction vehicles as they were building roads. So perhaps some of the material was brought in, but that's what we have here. At least deeper down, we should get perhaps the B horizons were not affected by anything that was closer to the surface. Let's move to the texture analysis, and here we have only had enough soil because our A horizon was very extensive. We were only able to do the hydrometer analysis of the constituents there, and it came up as 22% clay, 23.2% silt, and 54.8% sand. So it is quite sandy, and that to be expected if we see a hill nearby and material gets we get alluvial deposits, and if the parent material is sandy, so we expect to find more sand in this horizon. And as we go down to the B horizons, we only had to rely on our field texture method, which is less precise, perhaps biased when you rub the material between your finger, especially to distinguish the amount of silt and clay. The coarseness of sand is very easy to tell, but it was clearly clear using the field texture analysis method that it was very, very sandy, although we cannot attribute and give exact numbers of percentage of sand, we identified that B1 horizon as silty clay, so still quite a lot of silt in there, which is to be expected if the river would, if the creek would occasionally overflow its banks and deposit some silt in this area. And then as we go down to B2 was a clay loam, and go even deeper, we get in sandy clay. So that is to be expected from this area where we see both the effects of a hydrology in form of a creek occasionally overflowing its banks and depositing silt, as well as other material moving downhill, other colluvium moving downhill. So that is confirmation of the effect of both hydrology and topography on this particular samples. Okay, so let's move on to the next site. The last site was probably the easiest to identify. As we can see, it was getting a little dark, and there's my partner and my daughter sitting on a side of the hill, preparing to take the core, and the core came out as very typical incepti soil, where we only had a couple of 3 distinct horizons, and we went down in less than a meter down to the bedrock, which is a sandstone. And here we only have a less than 20 centimeters of a horizon that quickly transitioned to a very uniform C horizon, which is just broken parent material. And then on the very end of the auger, probably the last 2 centimeters of it was struck the bedrock. It's harder, but once you crush it, actually the bedrock and the weather parent material are not very distinguishable from each other, as we will see later on. So in this, because the slope is steep, it's well drained, we do not have any B horizons in this area. Whatever accumulates erodes and moves downhill and probably deposited at site 3. That's why we have higher concentration of sand. Let's see what we got using our texture analysis. Here again, we do not have enough soil to do a texture analysis in the hydrometer method, so we relied on a field method, as well as since we have quite a lot of sand, it was easy, it was relatively visual to see in the test tubes once we mix the soil and allow it to settle how much sand there is. And the A horizon was determined as loamy sand with a high sand concentration. The C horizon was determined again as loamy sand, although the color is different. There's probably the absence of organic material that gives the color, but as far as texture goes, they are similar. At least similar enough that you still name it as loamy sand. And you can see actually in the test tube on the left is our A horizon, on the right is our C horizon. Probably fair to say that there's more sand, or at least coarser sand, on the right side in the C horizon, which is to be expected, which is sandstone with probably some clay in between. So let's move on to our conclusion. And the conclusion is, as was to be expected apart from site A, is the material, the parent material, very similar. It's a sandstone, and we found basically the same kind of sand in all the lower horizons. We found typical incepti soil at site 4 with a very thin, barely formed A horizon, no B horizon, and a site 4. It's the slope of a hill. At site 3, which is located between the riverbed and a hill would assume that there would be effects of both the hydrology and topography, and would have deposits moving downhill, alluvial as well as alluvial deposits from the creek, and that the texture analysis more or less confirmed this hypothesis. And then at the river channel at site 2, that's a little bit above the normal water level mark, we found a lot of silt and clay, which is to be expected in this area. The site 1 is what was unexpected, since we were expected to find some clay condition below the current watermark, but it wasn't. Perhaps it's the clay layer there is very extensive, and the water doesn't have time to penetrate, and actually the modeling that I attribute to very light modeling doesn't go horizontally, but if we could see an auger vertically, so perhaps as you move away from the river channel, from the edge of the water, the water instead of fluctuating vertically up and down, it more or less fluctuate vertically, and perhaps that is why we did not find clay condition. And maybe if we would take sample directly into the creek, maybe there we would find, but that could be saved for another day. And that is our presentation. It was interesting to show the same parent material, same climate, same geographical area, just a few hundred meters away from each other, could produce distinct soils with its distinct properties. And although texture, as far as texture go, it may look very similar. However, when you look at each sample of the soil, as we saw in agar, and in texture, they are significantly different. And so texture would tell us only part of the story, the size of the grains, but there are other processes that go on that form the soils to be very distinct from each other in this area. So thank you for staying with me and listening to this lecture. I hope you liked and being informed, and it was a pleasure for me to present it. Thank you so much.